everyone, myself Dr. Vijaykumar, Associate Professor, Department of Electronics and Communication Engineering, Aditya University. In today's session, we are going to see the problems on multiple random variables. So at the end of this particular session, we will be learning the definition of joint density function, distribution function properties, and we will be solving practical problems on joint distribution and density function. So already we have seen these topics, joint distribution and joint density functions. We will recall them. So the joint distribution function is generally denoted as fxy of xy is equal to probability of capital X less than or equal to x. And it is generally described in terms of unit step function for a discrete version, p of xy, u of x minus xm, y of y minus n. And also we have seen the properties in the earlier sessions. The main property which we will be using is the fifth property, the probability of x1 less than x less than. If you want to compute the probability between any two limits, we will be using this property. And one more important property we will be using in the practical problems is when we are computing the marginal distribution functions, what we will do is if I want to compute the marginal distribution function of y, I will replace the value of x with infinity. If I want to compute the marginal distribution function of x, I will replace the y value with infinity. So here we use the two-dimensional plot for representing the joint distribution function. So here probability of x comma y values are given here at different locations, at 1 comma 1, at 2 comma 1, at 3 comma 3. You can see we already seen that the probability distribution function, joint probability distribution function can be expressed as sum of shifted versions of unit step function. Here also we have expressed in a similar manner. For at different locations the probabilities are given. You can see here the unit step function, the staircase function. So this is how we represent in the two dimensional the joint distribution function. So here x axis, here y axis, this represents the amplitude in the sense the probability value of fxy of xy. And also we have seen in the earlier session the definition of joint density function. The joint density function is the derivative of distribution function. It also can be expressed as sum of shifted versions of impulse function. This we will use in the problems. So to represent the joint density function, we use this representation. And also we use different properties of joint density function in practical problem solving. This one, area under the joint density function is unity, and if you want to compute the marginal density functions, we will doing the integration with respect to y, you will get marginal density function of x. If I am doing the integration with respect to x, I will get the marginal density function of y. And along with this, if I want to compute the probability over limits, I will compute the area under the density function over the defined limits. So these are the properties we will use in the practical problems. So let us see some practical problems. So the main learning outcome we are going to learn at the end of this session is we need to apply the concept of joint probability distribution function, joint probability mass function, joint probability density function concepts for practical solving. A problem is given something like this: the probability distribution function of two-dimensional random variable x and y is given. So the joint probabilities is expressed in terms of matrix. Now they are asking us to compute the marginal distribution function of x and y, and also they are asking us to compute some probability over a prescribed range. So the joint distribution function is given for different values 1, 2, 3, 4. So for example, this represents the p of x is equal to 1, y is equal to 1, which is equal to 0.1. So like this, all different data values are given to us. So using this data, we will compute the marginal distribution function of x and marginal distribution function of y. And see here, when I sum all these values, the sum of all these values is 0.3. When I sum all these values, the sum of all these values is 0.1. When I sum all these values, the sum is 0.5. When I sum all these values on the row, I will get. So when I add all these values, this value must be equal to 1. The sum of all probabilities defined on a random variable must be equal to 1 according to the probability mass function. Similarly, column wise addition, this 0.3, 0.1, 0.5, 0.1. Again you add, you will get 1. So the summation of probability of xi comma yj will be equal to 1. According to the joint probability mass function definition, the sum of all the joint probabilities must be equal to unity. So now here we are interested in computing the marginal distribution function of x and marginal distribution function of y. So for that we have computed the values when x is equal to 1, what is its corresponding value? When x is equal to 2, what is its corresponding probability? X is equal to 3, corresponding probability. X is equal to 4, corresponding probability. Like that we are calculated the x and y values. So to plot the distribution function, so if we express this in terms of distribution function, the distribution function will be something like this: 0.1 into u of x plus 4 y of minus 1 and like this. See, marginal distribution function. So this can be expressed as fxy of summation j I p of xi comma yj u of x minus xi into u of y minus yj. This is the joint distribution function. Now we are interested in computing the marginal distribution function of x. To get the marginal distribution function of x, what we need to do? We need to replace all the y values with infinity. So fxy of x comma infinity. So now fx of x will be equal to, this is first one, 0.3 into u of x minus 1, next 0.1 into u of x minus 2, next 0.5 into u of x minus 3, next 0.1 into u of x minus 4. When you sum all the values, we will get this one. Totally we will get 16 values. Summing the 16 values and identifying the same rows, we will get totally 4 values for marginal distribution function of x. Similarly, marginal distribution function of y will be fy of y is equal to 0.3 into u of y minus 1, 0.1 into u of y minus 2, 0.5 into u of y minus 3, 0.1 into u of y minus 4. Next problem is asking us to compute the probability of x less than or equal to 2, y less than or equal to 4. So the probability of x less than or equal to 2, y less than or equal to 4. So the total possible combinations which satisfy this relation will be x less than 2 and y should be less than 4. So 0, 1, 0, 2, 0, 3, 0, 4. This is for 0th row or first row. Let us say first row, 1, 1, 1, 3, 1, 4. Similarly, probability of 2, 1, 2, 2, 2, 3, 2, 4. All probabilities we need to add. Totally 8 probabilities. Adding all these probabilities, the value of this probability of x less than or equal to 2, y less than or equal to 4 is 0.4. So 8 combinations possible. 1, 1, 1, 2, 1, 3, 1, 4. This is when x is equal to 1. When x is equal to 2, 2, 1, 2, 2, 2, 3, 2, 4. I am keeping 1 as constant, x. Y I am keeping as constant, whereas x is making it as variable. Totally 8 combinations. The sum of all these 8 combinations is equal to 0.4. Next problem is given expressed in terms of unit step function. Earlier problem we expressed from the given data in terms of unit step function, whereas here the unit step function is given to us. Now we are expressing, now we need to compute the marginal distribution function of x and y and some probabilities, and also we need to plot fxy of xy, that is nothing but joint distribution function. So for the given data you can see here x is equal to minus 4, y is equal to 1, x is equal to minus 4, y is equal to 1. The corresponding probability is 0.1. Next, when x is equal to minus 3, y is equal to minus 5, the corresponding probability. When x is equal to minus 1, y is equal to 3, the corresponding probability is 0.17. Next, x is equal to 0, y is equal to 1, the corresponding probability is 0.05. Next, x is equal to 2, y is equal to minus 2, the corresponding probability is 0.18. Next, x is equal to 3, y is equal to 4, the corresponding probability is 0.23. When x is equal to 4, y is equal to minus 3, the corresponding probability is 0.12. Now they are asking us to compute the, first we need to plot the distribution function. Already I mentioned the distribution function plotting for different location. The plot will be a 2-dimensional plot. It looks like a sum of shifted versions of unit step function. Now we need to compute the marginal distribution function of x and marginal distribution function of y, and we need to plot them correspondingly. So to compute the marginal distribution function of x, what we need to do? We need to replace y with infinity. So when I replace y with infinity, u of infinity will be equal to 1. U of infinity minus something is 1. U of infinity plus 1 is 1. So all y values will become 1. Now 0.1 into u of x plus 4, 0.15, 0.17, 0.05, 0.18, 0.23, 0.12. So different values we got for x. So the x values ranges from minus 4 to plus 4. At x is equal to minus 4, it is 0.1. At x is equal to plus 4, it is 1. Similarly, if I want to compute the marginal distribution function of y, I need to replace x with infinity. So replacing x with infinity, u of x will be 1 for all values of infinity, and these values will be 0.1 into u of y minus 1, it's go on up to this one. So the y ranges from y is equal to 1, y is equal to minus 5, this is the least range, and y is equal to 4 is the maximum range. Y is equal to minus 5, y is equal to 4. So different steps based on these values. This is the marginal distribution function of y, marginal distribution function of x. And also they asked us to compute the probabilities for different ranges. So minus 1 less than x less than 4, minus 3 less than y less than 3. So we have got one property. If I want to compute the probability between any two limits, this is the formula I will apply. So based on this, the formula will be fxy of x2 comma y2 means 4 comma 3, x1 comma y1 minus 1 comma 3, x2 comma y1 4 comma minus 3, x1 comma minus 2. So these probabilities are already given to us in the form of table. Substituting it, we will get 0.23. Next, this problem is based on the continuous random variable, and this is based on the joint density function. So in the joint density function also, we have got one important property, the marginal density function of x and marginal density function of y. The marginal density function of x can be computed when I integrate with respect to y. When I integrate fxy of xy with respect to y, I will get the marginal density function of x. If I want to compute the marginal density function of y, I need to integrate with x. If I integrate with x, I will get marginal density function of y. So the given joint density function, now to compute the marginal density function of x, I need to do the integration with respect to y. Y limits ranges from 0 to 1. Doing the integration, we will get this value, and this is the marginal density function of x, and while writing that, we need to express the range for x 0 to 1. In a similar manner, marginal density function of y we are computing, we need to substitute the limits for x, x is equal to minus infinity, and we need to do integration with respect to dx. After doing that, we will get 6 by 5 into y square plus 1 by 2. The next problem is we need to compute the probability of y whose values are lying between 1 by 4 to 3 by 4. So once we computed the marginal density function of y, we can compute the probability density function of y. Probability density function of y is equal to y less than y2, y1 to y2, fy of y dy. Applying this property, so substituting all this value calculation, we will get 0.4625. This is the based on the marginal density function of y, we are computing the probability, because the probability is asked for y variable only. Next, another problem, joint probabilities of two random variables x and y are given. In this problem, they are asking us to compute joint capital PDF, next small PDF, and marginal PDF and marginal small PDF. All parameters are covered. We need to express the joint probability distribution function, joint probability density function, and also we need to compute the marginal distribution function, marginal density functions of x and y. So first, for the given data 1 comma 1 it is 0.2, 1 comma 2 0.15, 2 comma 1 0.1, 2 comma 2 0.2, 3 comma 1 0.2, 3 comma 2 0.5. These are the probabilities given to us. Now if I want to compute the joint distribution function. I can express the joint distribution function in terms of unit step function. Now it is expressed as 0.2 into u of x minus 1 u of y minus 1 plus 0.15 into u of x minus 1 u of y minus 2. 0.1 into u of x minus 2 into u of y minus 1, 0.2 into u of x minus 2 u of y minus 2, 0.2 into u of x minus 3 u of y minus 1, 0.15 into u of x minus 3 u of y minus 2. So, like this we can express. Now, to compute the marginal distribution function, we need to replace y with infinity to compute x. To compute y, we need to replace x with infinity. So, substituting it and simplifying all these things, you can see here x minus 1 is repeated 2 times. So, that is why 0.15 plus 0.2, 0.35. X minus 2 is also repeated 2 times, 0.1 plus 0.2, 0.3. X minus 3 also repeated 2 times, 0.15 plus 0.2, 0.35. Next, similarly here also in place of x we substitute infinity, and after substituting again reorganizing them. Here y minus 1 terms 1, 2, 3. Now we need to add all this 0.2 plus 0.1 plus 0.2, 0.5. Next 0.15, 0.2, 0.15, 0.5. Now we need to see the plots. So this is the plot of joint distribution function, this is the plot of marginal distribution function of x, this is the plot of marginal distribution function of y. And similarly, to compute the joint density function from the distribution function, the joint density function is the double derivative of joint distribution function, derivative with respect to x and y. So when you derivate a unit step function, what we will get? An impulse signal. So we replaced the unit step function with impulse signal in the joint density function representation. Here also what we will do is, in place of y, if I replace infinity, marginal density function is the derivative of marginal distribution function. Similarly, marginal density function of y is the derivative of marginal distribution function of y. So the corresponding plots, impulse function plots. This is the 2-dimensional joint density function. So we will draw on a plane. This is the joint marginal density function of y, marginal density function of x. So in this session what we have seen is we recall the basics like a joint distribution function definition and the properties, joint density function definition and its properties, and later on we have seen some practical problems, how to solve these problems in a practical scenario we have seen. So in the next session we will see the operations on multiple random variables. Thank you.